Lesson 9-4, graphing rational functions. A rational function has an equation in the form of f of x equaling a times a of x divided by b of x, where a of x and b of x are polynomial functions, and b of x cannot equal 0 because that's in the denominator of a fraction. Reviewing our vertical and horizontal asymptotes, if f of x equaling a of x divided by b of x, a of x and b of x are polynomial functions with no common factors other than 1, then b of x cannot, and b of x can't equal 0, then you have these properties. F of x has a vertical asymptote whenever b of x is 0, and f of x has at most one horizontal asymptote. It has at most no more than one horizontal asymptote if the degree of a of x is greater than the degree of b of x. There's no horizontal asymptote. If the degree of a of x is less than the degree of b of x, then the horizontal asymptote is y equals 0, which is the x-axis. So that second part means if you have let's just say we had x over x squared. The previous one would have been like x squared over x. And then the third statement says if the degree of a of x equals the degree of b of x, then the horizontal asymptote is the line y equals, and then you take the leading coefficient of a of x divided by the leading coefficient of b of x. So this would be like, say, if x was divided by x, whatever number is in front, so if this was 2x and this was 3x, then the horizontal asymptote would be at y equals 2/3. So our first example, Young's rule can be used to estimate the dosage of medicine to give a child if you know the adult dosage of the same medicine. Young's rule can be written as y equals ax divided by x plus 12, where a is the adult dosage in milligrams and x is the age of the child in years. So we're going to graph, find the key features, and then use the graph to evaluate the rest of the problem. So part A, we're going to graph the function. They're giving us the function for an adult that's 200 for an adult, a dose of 200 milligrams is needed. So we're going to put 200 in for the A, because that's the adult dosage. And the original function said x plus 12. So this is our function that we're going to graph. Now we're going to have a vertical asymptote at -12. So here, let's count by sixes. So if this is 6, this would be -12. So let me label this one. So we're counting by, so this is -6, -12, -18, and this would be -24 and so on. So 6, 12, 18, 24. And then our y's, let's count those by, we can count those by 100. Okay, so now I'm going to grab my calculator here, and we're going to put this in our calculator to come up with our table of values. So our y equals, we have 200x, then we're going to divide that by parentheses x plus 12, and parentheses, and then if we graph that, we'll have to change our settings, but I just want to get to the table so then we can graph points here. So we have a point at 0, 0, so let's put a point there. We have a point at 0, 0. We have a point at 340. So 340. Since we're counting by sixes, half of 3 would give us, actually let's just count by sixes. So let's go 6 will give us 66.67. If we're counting by 100s, that would give us, um, actually before that, we have to do the horizontal asymptotes. So the degrees are 1 and 1. So that means I take the leading coefficient, 200 divided by 1. So I need a horizontal asymptote at 200. Since I'm counting by 100s, I would have a horizontal asymptote right here. So my vertical and then my horizontal. So I'll point at 0, 0. 6 is at 6 and then 66. So that would be roughly here. Because if we're counting by 100s, and then if I go to 12, make this easier, let me set up my windows so it'd be counting by 6s. Now a second graph. Actually, I need to start at 0. Okay, now 12 is at 100. That would be here. And then we have 18 is at 120 there. 24 is 133. So then it just keeps getting closer. If I were to go up to -6, that's a -200. -6 to -200 would be right here. And if I went up to 12, there's an error message because that's the asymptote. So this one would look like this. And then on the other side, if I continue, -18 and 600. So -18 and 600, that's 1, 2, 3, 4, 5, 6. Then we have 24, -24 and 400. So 1, 2, 3, 4. -30 and -300. So 1, 2, 3. So about here. 36 would be 300. So that'd be 1, 2, 3. So this one looks something similar to this. So there's our graph. Now let's do the intercepts. So the intercepts would be 0, 0. Increasing, this is always. And here we would just say x has to be greater than or equal to 0. Decreasing, never. Positive when x is greater than 0. Negative when x is less than 0. End behavior as x approaches positive infinity, y approaches 200. And as x approaches negative infinity, y approaches 200 as well. Okay, now we're going to use the graph. It says find the dosage for a 12-year-old child if the adult dosage is 200 milligrams. So here I would just put 12 in for x. So since I have it on my calculator, if I go to graph and I hit change my Windows settings, let's do the x maximum, let's do 80, count by tens. And the other one, maximum, it looks like let's go up to 600, count by 100s. Now we can graph it. We'll see that there, and then hit second, trace, find the value, number 1, when it's a 12-year-old. That gives us 100. So the dose would be 100 milligrams for a 12-year-old. Next, trains travel at different velocities because of conditions of the train, the curvature of the track, or the railroad crossings. The average velocity v of the train is v equals vt or V1 T1 plus V2 T2 divided by V1 plus V2, V1 plus T2, where V1 and V2 represent the velocities of the train for a period of time, T1 and T2 respectively. Suppose a freight train travels at 60 miles per hour for 4.5 hours and 35 miles per hour for X hours. We're going to create a function first. So to create the function, I substitute the numbers in for our function here so you can see what we have. We're going to simplify that so then we can write that down. So 60 times 4.5 that gives us 270. So this would be 270 plus 35t all over 4.5 plus t. Now we'll grab our calculator. We'll put that in there. So 270 plus, actually, let me put that in parentheses. So we have 270 plus 35x, and parentheses, divide that by parentheses 4.5 plus x. If I hit graph, there you can see our graph here. So seconds, table. So let's see. Right now mine's counted by sixes because we changed that before. For this one, let's count the x's by fives and the y's by tens. So let's go here. So let's go negative 20 to a positive 20. Count by fives. And the minimums, let's go negative, we go to negative 80 to positive 80. We'll count by tens. Then graph that. Okay, there we can see that. Change our table settings. Let's go 0. We're counting by fives. So second trace. Okay, so our asymptotes are going to be, so if we use our calculator to find the asymptotes, to find where there's an error, it would have to be at negative 4.5, which we're not going to see on there because of how I set up the there. So a negative 4.5 is the vertical asymptote. So if we're counting by fives, this would be roughly here. And if I look at it, I have a t and a t, so this would be 35 over 1. So I would have a y-intercept, or the horizontal asymptote at 35. So I'm counting by tens, so it would be 10, 20, 30, 40, so 35 would be here. Now we can plot our points. So let's do 0. We had 0 and 60, so 0 and 60 is 10, 20, 30, 40, 50, 60. It's here. We did 5, and that's 46. So 5, 10, 20, 30, 40. That'll be roughly here. 10 is 42. 15 is 40. So this one will look like this. Come around here. And then if you go to the other side of 0, so we have negative 5. Would be a negative 190. So that would be way down here. Then we have negative 10 at 14. So negative 10 at 14, since we are coming by ones, or coming by tens. So this would be roughly here. 15 is at, actually, Negative 10 would be 14, so roughly here. Negative 15 is 24, so roughly here. Going up, 27, so here, 29. Then you're at 30, so it's going to come like this. So there's our graph. Now the key features, the intercepts. There is an intercept right here, so we can find that one. But that one wouldn't make sense for our particular problem, but let's just find it anyways. So if I go to graph, seconds, trace, second trace, 0. You have to go to the other side. Above the x-axis, below the x-axis. So it's negative 7.7. The y-intercept, whereas across the y-axis, looks like 60. Increasing, never. And decreasing when, so always, except for when x can't equal negative 4.5. Positive, when is it above? When x is greater than. See, when x is less than negative 7.5, and when x is greater than negative 4.5. Negative when x is less than negative 4.5, but greater than negative 7.5. End behavior as x approaches positive infinity, y approaches 35. As x approaches negative infinity, y approaches 35. And I'll use that to answer the question. It says find the amount of time the train travels at 35 miles per hour if its average velocity is 45 miles per hour. So here to find this one, if we go back to our original function where it was b equals, it was 270 plus 35t, or 35x equaling 4.5 plus t. The velocity here, they're telling us the average, or v, the average was 45. So if I use this, I can now multiply this side by 4.5 plus t, just so I can get this away from the denominator. It means I multiply that by 4.5 plus t here. If I distribute, 45 times 4.5 gives me 202.5 plus 45t equals 270 plus 35t. Get the t's to one side, so I'm going to subtract 35t on both sides and then subtract 202.5. I now have 10t equals 67.5. Get t by itself by dividing by 10. The time would be roughly 6.75 hours. Now if I look at the graph here, if I find like 45 would be roughly, since this is 50 here, 45 would be roughly here. If I go straight down, that's roughly where the 6.75 would be. Going to our next problem. Use graphs of rational functions. It says the cost y of an x-day ticket to an amusement park is y equals 12x plus 35. We want to graph the function. Graph A function that represents the average cost per day of a ticket for a ticket. Part B, find the key features, and then C, use the graph to find the average cost per day for a 4-day ticket, round to the nearest cent. So for this one, we need to graph this one. So we have y equals 12x plus 35 for x days. We want to find it for one particular day or per day. So I'm going to divide that by x. So that is actually going to be our function here. Now if I take my calculator, let's go to our y equals and let's type that in here. So this is 12x plus 35. And we're going to divide that by x. So if I hit graph, you can see our graph here. Let me check my table set. So we're going to just count by ones here, hit graph. Okay, so now second graph, let's look at a table. So the asymptote is at 1, and our vertical asymptote is at 0, and our horizontal one is at 12. So let's count by, so let me just scroll all the way down here. Okay, so our vertical asymptote is at 0. Our horizontal one is at 12. So let's count this by, we count these, our y's by, we count the y's by 12s. So actually let's count by 2. No, let's count by 6s. So 12 would be right here. Now let's plot our points down. So if we did 1 would be at 47. So 1 and 47 would be, if we're counting by 6s, 6, 12, 18, 24, 30, 36, 42, 47 would be way up here. 2 would give us 29.5, 6, 12, 18, 24, 30, so roughly here. And then we'd have 3 and 23, so that would be just underneath here. And if we went to 4, that's 20. So 6, 12, 18, so roughly here. The next one would be 5 and 19. So here, and then 17 be roughly there. So this is going to come down roughly looking like that. And if we went the other direction, -1 and -23. So -6, -12, 18, 24, 30. So this is 24, -23 would be here. -5.5 would be probably here. And we had 3 would give us 0.3. Then the -5 would give us, actually 4 would give us 3.25. So here, -5 and 5, so that'd be roughly there. Then -6 and 6. Then -7 and 7, so it goes up something like this. There's our graph. So our next parts, find the key features, the domain. X is all real numbers except for it can't equal 0. The range, f of x is all real numbers except for it cannot equal 12. The x-intercept, where is it across the x-axis? If I go back to our graph, the second trace, number 2, the 0, the x-intercept. Enter, go down, enter, enter again. Gives us -2.9. the y, there is no y-intercept, so none there. Increasing, it's never decreasing when for all values of x except for x cannot equal negative 2.9. Positive above when x is less than negative 2.9 and when x is going to be greater than 0. Negative would be when x is between, when it's greater than negative 2.9 but less than 0. In behavior, as x approaches negative infinity, f of x approaches 12. As x approaches positive infinity, f of x equals or approaches 12 here. Next part, use the graph to find the average cost per day for a 4-day ticket, round to the nearest cent. So if we put a 4 in for x, so if we went to our calculator and did the value, so second trace number 1, find the value, put a 4 in there, gives us 20.75, so approximately $20.75. Next part, comparing rational functions. Consider g of x, which is the quantity x minus 2 divided by quantity 2x plus 2. So if I think of that, if I write that down, this would be quantity x minus 2 divided by the quantity of 2x plus 2. And the rational function h of x is shown in the table. We need to graph both of them and then compare the key features of g of x and h of x. So first, let's graph g of x. So g of x, grab our calculator here. Y equals, so this is going to be x minus 2 divided by the quantity of 2x plus 2. If I hit graph, let me change my settings. And use a table feature to come up with some points here. So the y-intercept or the vertical asymptote would be at struct 2, then divide by 2. That'd be a negative 1. We have at negative 1 a vertical asymptote. And then the horizontal one, since they're both a degree, this would be at 1/2. So half would be right here. So there's the horizontal asymptote. Now let's choose some points on each side of negative 1. So I'm going to put a point at negative 2, 2. So negative 2, 2 would be here. We have one at, let's do negative 4, 1. So this one's going to look like this. Back up here. And then if we did the other side of negative 1, so 0, negative 1. So 0, negative 1 would be here. And we have 2, 0. 4 and 0.2, so we can just start writing this direction. So that's g of x. Now let's do h of x. So we'll put these points down. So -2, 0, -1, -0.5. We got 0, -2. We have 1 is undefined. So that means there's a vertical asymptote here. Let me do that a little better. 2, 4. So 2, 4 would be 1, 2, 3, 4. We have one at 3 and 2.5 be here. Then we have another one at 4, 2 be there. And if we think about where looks like the horizontal asymptote would be at 1. So our graphs would look like this, and this would look like that. Now we can do some comparison. So comparing the two, the domain for g of x, this would be -infinity on the low end to -1. And then for here would be -1 and positive infinity. So this one is just saying every, let's just write this simpler. So this would be x such that x is all real numbers except for it can't equal -1. The other one would be x such that x is all real numbers except for x can't equal, if I go back to that one, x can't equal a positive 1. A range for the first one would be, for g of x, would be y such that y is all real numbers, but it can't equal 1/2. And the other one would be y such that y can't equal a positive 1. The x-intercept for g of x is 2, for h of x is -2. Y-intercepts are -1 and -2. Increasing or decreasing, this one is increasing, but x cannot equal -1. And the other one is decreasing, where x cannot equal positive 1. And then positive, negative, positive. So this one is positive when, let's see, -infinity to -1. And when you have 2 to positive infinity. And the other one would be -infinity to -2 and 1 to positive infinity. Negative, when is it negative? This one between -1 and positive 2. And this one is -2 and positive 1. End behavior, as x approaches -infinity, g of x approaches 1/2. As x approaches positive infinity, g of x equals 1/2. The other one would approach 1. And the vertical asymptotes, -1 and 1. Horizontal asymptote is at 1/2 and 1. Next part is graphing rational functions with oblique. An oblique asymptote or a slant asymptote, a function is a line that is neither horizontal nor vertical and is approached by the graph as x approaches positive and negative infinity. So you can see we have our horizontal asymptote. That is actually going to be a line. So how do we know if you have a horizontal or oblique asymptote? So if f of x equaling a of x divided by b of x, where a and b are polynomial functions with no common factors other than 1 and b of x is not equal to 0, then f of x has an oblique asymptote if the degree of a of x minus the degree of b of x equals 1. So if they're 1 apart, the equation of the asymptote of b of x equal to a of x over b of x with no remainder, that will be our equation there. In some cases, graphs of rational functions may have point discontinuity, which looks like a hole in the graph. This is because the function is undefined at that point. If the original function is undefined for a of equals a, x equals a, but the related rational expression of the function is in simplest form is defined for x equal a, then there's a point discontinuity or a hole in the graph at x equaling a. If f of x equals a of x over b of x and b of x equals 0, then x minus c is a factor of both a and b. Then there is a point of discontinuity at c. So that will make a little more sense once we do some graphing. So here it says, consider f of x equaling x squared plus 2x plus 1 divided by x minus x plus 4. First thing we need to do is we're going to find the zeros. And to find the zeros, all you need to do is look at your numerator, and we are going to factor those. That's a perfect square trinomial, which would be x plus 1 times x plus 1. And so if I make those equal to 0, I would get x equaling a negative 1. So I have a 0 at x equaling a negative 1. So that would be one point where it crosses the x-axis. Next part, I'm going to find the asymptotes. So to find the asymptotes, the vertical asymptote, I look at the denominator, and the vertical asymptote is going to be at x equaling a negative 4. The other ones, see, because the degree on the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. So now, and the difference between the exponents 2 and 1 is 1. So I am going to have a oblique asymptote, or oblique asymptote. So what I'm going to do is I'm going to do the division for it, so then I can find what the equation of the line would be. So to do that, I'm going to do long division. So I have x plus 1. And I'm going to divide that by x squared plus 2x plus 1. So I need an x, so this will give me x squared plus 1x. And I subtract below. So when I subtract, I change the signs. So this will give us 1x plus 1. To get that exact one, I have a plus 1. So that would give us x plus 1. When I subtract below, I change all the signs and I get 0. So this x plus 1, actually this is a 4, so I got to change that. This would be 4x. And subtract, that will give me a negative 2x. This would be a minus 2. And that will give us a minus 2x and a minus 8. Now when I subtract below, I'm really adding. So this will give us a 9, but I'm only referring to up here. So let me erase this so you can see that better. So this is x minus 2. So the x minus 2 is what I'm going to graph for my asymptotes. If I come to my graph here, I need a vertical asymptote at negative 4. So 1, 2, 3, 4. I need a point at negative 1 on the x-axis, negative 1 here. So I'm going to put a point here. And then the vertical asymptotes, I'm going to graph the x minus 2. That means it crosses the x-axis at -2. So I'll just put a point here. So up 1 over 1 is a slope. So if I drew the asymptote here, it will look like this. Now I'm going to use a line to come up with other ones. So I come up with a table of values. So I'm going to do that with my calculator here. I'm going to type in the equation. So in the numerator, I have x squared plus 2x plus 1 in parentheses divided by x plus 4. And then hit second, graph, see a table of values. I want to get to -4, so I need numbers on both sides of -4. Okay, so I can plot a point at -1, 0. So -1, 0, I have that. I have a point at -2.5. So -2 and 0.5 is here. Then -3, 4. And then I can do, if I went down, if I put the 0, 0 is 0.25, 1 is 0.8. So this is going to come like this. Going to wrap around. And it's going to come up like this and follow. And the other one, if I go the other direction, so up here, -5 and -16. So -5 and -16 is way down here. So this one I don't have as much room, but it's going to look something like that. So that would be our graph here. Next, let's graph this one with an oblique asymptote. So first part, find the zeros. Look at the numerator. I have zeros at x equaling a -1. The asymptotes, I'm going to have a vertical asymptote at -3. And then to find the horizontal oblique one, I'm now going to have x plus 3. I got to divide that by x squared plus 2x plus 1. So I need a x here, so that'd be x squared plus 3x. Subtract these, and that gives me a -x plus 1. So I need a -1 here. That gives us a -x minus 3. Add the opposite down here, and that gives me 4. So I need to graph x minus 1. So I'm going to put a point here, up 1 over 1, so that'll be like this. So here's my oblique asymptote. My vertical asymptote is at -3. And now I can use my graph, plot some points down. So let's use the calculator for that one. So go to y equals. This I'll just make it as 2x plus 1, so that's the same, and then it'll be x plus 3. Second graph. So let's do -5 and -8. So -5, -8 would be way down here. Then we have -4, -9. So -4, -9 down here. So this one is going to look something like this down here. And on the other side of -3, we have -2, 1. So -2, 1 is here. we have -1, 0 here. We have 0 and 3.3. So this one's going to come down, wrap around, and then come back up this direction. So that's just a rough graph of it. If you want to see that on the graph here, you can see the vertical asymptote or the oblique asymptote would be right here. So that would be an idea of what the graph would look like. Next graph, this one with an oblique asymptote. So we have vertical asymptote at -1/2. We have zeros, so let's find the zeros on that one. Actually, we just need to find the asymptotes of this one in the graph. So the oblique, we have 2x plus 1. So do the division. It would be 2x squared plus 3x plus 2. Multiply this by x, and that gives me 2x squared plus 1x. Subtract below, and we get 2x plus 2. And then I need this to be a plus 1. So it'll be 2x plus 1. Subtract below, and we get 1 as a remainder. Here's our oblique asymptote. So if I put that in there, crosses at +1. Right here, up 1 over 1. Draw that line through here. Those are our asymptotes. Now if I take my calculator and let's graph that one. So y equals, this is 2x squared plus 3x plus 2 in parentheses, and then divide that by 2x plus 1. We graph that one. Okay, then second graph, come with our table. Vertical asymptote is at -1/2. So let's put a point at -1, -1. -1, -1 would be here. We have 0, 2 be here. We can have one at we can go and let's do -2 and -1.3. So -2 and -1.3 would be here. This one's going to look something like this, and this one's going to look like that. Next, example 4, graph with point discontinuity. Find the point of discontinuity. So we're going to graph this. Do this one to find the vertical asymptote. The vertical asymptote is at -2. This would have a horizontal asymptote, or an oblique asymptote. So if I did x plus 2 divided by x squared plus 0x minus 4, I would have a 1, or just plain x. That'd be x squared plus 2x gives us a minus 2x minus 4 minus 2 gives us a minus 2x minus 4. Add the opposites, it gives us 0. So our oblique is at -2. I drew this line through here. Now to graph that one, So here I have my line. I'm going to, if you notice right here, it hits the asymptotes. So for here, I need to put a hole at this point because the asymptote goes right through here. So when we're graphing with a point of discontinuity, we would say that the point would be at -3. So anytime they ask you to graph the point of discontinuity, you're graphing the horizontal or the oblique asymptotes, so that line, and then you are going to have a hole at the mark where it crosses the x-axis. So this is not -3, sorry, this would be -2 because the asymptote is at -2. Try another one. Here we need to find the line. So we have x minus 1, divide that by x squared plus 2x minus 3. So this would be x squared minus x, add, and that gives you 3x minus 3. So this would be a plus 3. 3x minus 3, add the opposites. That gives us 0. Here's our equation we're going to graph. The asymptote is at positive 1. So if I put a dashed line here, just to highlight that, and then I'll delete that or erase that. So I have plus 3, a point here, and then it goes up 1. Now here, I have an open circle here because that's the asymptote. It can't equal that, it's undefined there. And there's my line. And point of discontinuity would be x equaling 1. And our last one here. Doing the same thing here, find the point of discontinuity and then graph the function. So we have x plus 3, divide that by x squared plus 6x plus 9. Need an x squared, or just a plain x. That would be x squared plus 3x. Subtract below. That gives us 3x plus 9. Get plus 3. So 3x plus 9. Subtract below. And we get 0. Graph this one. The asymptote is at -3. So I'm going to put a point at +3. Slope of 1. So when x is -3, so if I go to x is -3, I have a hole here. And there would be my equation. And our point of discontinuity would be x equaling, that would be at -3. That's our lesson on graphing rational functions.